Okay, let's get started. Into the dark. So I have a question for you all. Why are we here? Right? I'm here. Very simple question, but yeah, many answers. I'm here to talk to you about how I research the universe. You may be here because you want to, at least I hope you're here because you want to listen to this talk. Right, so a very simple question, but many, many answers. Me as a cosmologist, the here and now is not really what my research focuses on. So when I ask the question, why are we here? It's not about here, great festival by the way, but it's not about here and not about now. It's really much more fundamental, right? We can ask, why is there shapeshift? Many good reasons to have a festival like this, but I want to go deeper, right? In the end, if we keep asking why, we end up with why are we here? Because there's a universe. Because without a universe, clearly we would not be here, right? It's the most essential question you can ask. Why is there a universe? So why are we here? Some may be here to hear the answer. I'm sorry, I don't know. I don't know why we're here. Another question for you. For that, I do have a good answer, and I wonder whether you have the answer. It's something you probably have all noticed, but why is it dark at night? So most people will say, it's because the sun sets, right? Because if you go rise early when you're at the Black Sea and it's still dark, you look east, and the sun comes up and it becomes bright. But again, it's a very simple question, but it turns out the answer is a little bit more complex. And last week I read a nice quote by Daniel Kahneman, who said, thinking is to humans as swimming is to cats. We can do it, but we don't like it. And most of our thinking is very lazy, because of course we say, it's dark because the sun has set. But when the sun is set, when it's on a dark place, what do you see when you look up at the sky? Is it truly dark? No. You see stars. The sun is a star like any of these other stars. The sun happens to be very close. But if we could have a universe with many more stars than we have today, than we can see, it actually, no matter where we would look, our line of sight would hit the surface of a star. So the reason it's dark at night is because we see so few stars. In a universe that had an infinite number of stars, it would be during the night as bright, if not brighter, as during the day. When we say, it's dark at night because the sun has set, what we're doing is, we see indeed a correlation, because when the sun sets, it's dark, and then when it comes up, it's bright again. But there's an assumption in the answer that most people give, because it's dark at night because what happens at night, not what happens when the sun is up. And so that's what you see. Often very simple questions, the questions I work on, have very complex answers. And that's, of course, good for job security. And so things are not so black and white. So let's bring some color into this whole story. Because people have been asking these questions for a long time. Here's an old medieval print where somebody is saying, let's explore the skies. What can we imagine there? And people were using their imagination to figure out what the world looks like. We're going to do something different here because we have a book of rules, the foundations of modern science, the work by Galileo, Copernicus, and Newton, and there's some modern work as well. And so sort of these rules, the logical reason that will apply to the universe leads to surprises, but also technology, because technology, we've heard a lot about sort of the artificial intelligence, but also physical technology like the invention of a telescope plays an important role in science, because when we look at the night sky, we see stars when we look at our naked eye. But the invention of the telescope has transformed our view of the universe. The universe is not made of stars. It's made of course, galaxies are made of stars, but the building blocks of the universe are the galaxies. It's a completely different universe when we look with telescopes at the sky. So people have been asking the question, why are we here, for a very long time? And I like this quote by Einstein because it gives some hope that there's actually a way forward to try to at least to answer this question. So we can try to comprehend the universe. Probably at the end of the talk, you probably think we're failing terribly, but we're trying our best. So going back, right, the connection between us and the universe has been there forever. As I said, people have been asked this question, why are we here? Because we notice that things are changing. Our daily rhythm is determined by how fast the Earth spins around its axis. That determines when the sun sets and rises again. The day is determined by astronomical events. The seasons are determined by the Earth going around the sun. And so it's not a surprise that pretty much any continent where people have been living, people have built observatories for different purposes than we build them now. Our new observatories look a little bit different, but they were intended to very practically know when you need to sow something, but of course they also led to a connection between us and our place in the universe. And I call this the TikTok universe because we tend to project our own self-importance on the universe. So when people started thinking about the universe, they look around, it's like, I must be the most important. I'm clearly more important than animals. So people put themselves in the center. And despite all the progress, people still think that, right? The TikTok, the social media is about making you the center of your universe. And so people go for perfection. Circles are the most perfect objects. And so people thought the universe is circles revolving around humans. And we still do this. So I really like this. In Bulgaria, people go out in the mountains, make circles of themselves, and try to connect to the universe. And so these rituals play an important role, both in sort of making the connection, but also in art. Right? Stravinsky, the Sacre de Printemps, is a ballet set to celebrate an old ancient ritual. And so that led us to, because we like modern dance, that a couple of years ago, after performance, my wife sort of urged me that I should work together with the Nederlands Danstheater, one of the top modern dance companies in the world. And how do you do this? And so I came up with the idea, well, a lot of the work I will show you in the rest of the talk is recent discovery. Pretty much all our modern views of the universe 100 years ago, this talk would have been completely different. I would have ended with the Sacre de Printemps, which is about 100 years old. That will be it. We've learned a lot, and that was the idea, to talk to choreographers, top dancers, composers, and see what would happen if we talk about our modern view of the cosmos, and how would that inspire them again? Because that link between dance as a way to express our connection to the cosmos is ancient, but it's time for modernization, and of course the way they dance is very modern. And in the end, and much of the talk is sort of linked to what I showed there, is on how we do science. Because I'll just show you the final result, and you'll be like, this guy is nuts. So, most of the time when people hear science, they will look like this, right? But this cat can swim, so you can think. So bear in mind, you should be able to do it. You can do it. So let's just give you the answer. The universe we live in is very, very strange. It's very different than what we experience with our own eyes. So technology has played a very important role. And this was really the key bit also with the dance company, that our view of the universe has changed dramatically. We now know that the universe is incredibly dynamic. Everything moves in the universe. One of the choreographers was astounded, like nothing is standing still in the universe. You may be sitting still in this chair, but we're moving with 220 kilometers per second around the center of the galaxy right now. The Earth is not sitting still. And we know that the universe is expanding. 100 years ago, we did not know this, but we discovered that the whole universe is expanding, And that means that it was smaller in the past. And in the past, it must have been at some point so small that the whole universe fit in the smallest possible of spaces, something we call the Big Bang, the start of our universe. But the universe is dynamic. And so we know now that the universe is very big. There's billions of galaxies in the universe. This Big Bang, we actually know pretty well how long ago that happened, 13.8 billion years ago. Something as a little aside, we also know that all elements in your body, except for the hydrogen and lithium, if you take it, was made in the Big Bang. Every single other element, all the carbon, nitrogen, phosphorus, oxygen, was produced in the centers of stars that have since exploded. So this famous quote by Carl Sagan, we're all stardust, right? We are made of the recycled products of stars. But that we understand, the physics of that we understand, but in recent years we've come to learn that things are actually much stranger, and that's what my research focuses on. Most of the mass in the universe is invisible, literally invisible. You cannot touch it, you cannot see it, you cannot experience it directly. And worse, because we always thought that was it, that was weird enough, but about 25 years ago, we discovered that the universe, the expansion, is not slowing down, which is what we expected, but is going faster and faster and faster, and we have no idea why. Well, we have some ideas, but none of them is really good. So it's a nice example that the more we've learned about the universe, the less we understand. Again, very good for job security, but at the same time, yeah, you may wonder. And in particular, the question you should be asking is like, why should you believe me? Because this sounds ridiculous, right? Like, you could not have imagined this. This is exactly the difference. People had been projecting their own experiences on the universe, but when we look at the universe, it's completely different. I hope you know what this picture is, right? You see this white speck there? That's us. That's Earth in space. So this is one of the important things. We've learned that there's this vast universe and we're living on this very fragile planet which we should take care of. But really, why should you believe this? And that's where observation, scientific reasoning comes into place, because people were quite soon aware that if you can look at where the planets are. Here we see a picture taken every 24 hours, and then you see the position of Mars on the sky. If everything revolves around us, then sure, Mars moves around on the sky, but what it cannot do is go back and then go forward again. That's what we see here, is move forward, and then suddenly decides to go a little bit back before it continues again. That cannot happen in a universe where objects move on circles around us. So what do you do? Right? This is the classical challenge. You solving this puzzle, and so what do? You look at this piece, and the human tendency is to make sure it fits. You can either see maybe the backside is blue, so that would work, or you get some paint and make it blue. You force it to stick to your belief, because you believe this is the last piece of the puzzle. And so that's what I call the conspiracy theory approach. So people stick to their original beliefs, but make the model more complex. And that's what people did. They say, oh, things move on circles. So to explain the motion of the planets, they move on circles, what we call epicycles. And then you can explain that, what we call retrograde motion. So if you have a circle on a circle, that works. But it's a more complicated model, because now we start from two circles, or one circle to two circles. The problem is when technology advances, measurements get better, you needed ever more circles. Every time somebody did more measurements of the orbits of the planets, other circles needed to be added. So it became a circle upon a circle upon a circle upon a circle. So where does it end? And so Kepler sort of changed the whole story by saying, who cares about circles? He made it uglier but simpler. He assumed things move on ellipses. Like ellipses are not necessarily ugly, but less perfect than circles. And he moved the center of the solar system to the sun. So he basically said it's much simpler if the planets move on ellipses around the sun rather than circles around the Earth. So it's a very simple model that could explain much better data, and it formed the basis of Newton's theory of gravity. So this is really at the heart of science. We do the opposite of conspiracy theories. We like the simpler model, no matter how uncomfortable it is. A simpler model that explains more is always better. And so, thanks to that simple thought, you have an iPhone in your pocket. And this is the phases of Venus that Galileo saw with his telescope, which is impossible to explain, again, in this Earth-centric model. Yet the church put him in prison for saying that. So times have changed. And so this really was the start of the scientific revolution. So Newton basically devised his theory, derived, sort of reverse engineered, and showed that his law of gravity naturally would explain that planets move on ellipses. But more, and we sometimes don't appreciate, he linked the physics on Earth to the physics in the universe. So he basically says, it's universal. So I can study how apples fall on Earth, and that's the same physics that tells me how planets move around the universe. So physics is universal. That's really a base assumption. So this is how I extrapolate what we know about physics to the universe as a whole. But from the start, there were issues, and this is what is always where we get interested as scientists, right? We do like to swim and try to say, why is that? Because Newtonian gravity works really well. You can land objects on the moon, on planets, planetoids, meteorites, asteroids, whatever. It works really, really well. But we don't, at least people, we're not sure how does it work? How do these planets feel each other gravity? Like how does that work? How is that force transmitted? But it was also a very nagging observational thing, because as measurements got better, so planets move on ellipses, but these ellipses are fairly stable in time. So the ellipse is more or less always, the closest point to the sun is always the same point, and the furthest point is the same, except for Mercury. Mercury's orbit precesses, as we call it. It basically creates this rosetta. And we know that interactions between planets can cause this. And so people say, maybe there's another planet very close to the sun, so close that we cannot see it. They called it Vulcan, because it must be very hot there. And they tried to search for it, and they couldn't find it. It's really annoying. But gravity really worked so well, right? So they sort of ignored it. So it was there, everybody knew about it, but you don't talk about it, right? It's like most family gatherings, there's always something like that. Right, but there were conceptual problems, and that bothered Einstein. It's Einstein that really then solved all these conceptual problems with his general theory of general relativity, which is very important, by the way, for GPS. So without Einstein's theory, GPS would not work. But one of the first things he calculated was the orbit of Mercury, and he got the right answer. So that really, he has an, I would say, uglier theory. It's a very complex theory. It's ugly in that sense, although mathematically really beautiful. But it explained much more. It explained everything. It explained much more than this. And so this is important. This is how we make progress. We don't learn from confirming things. We learn from inconsistency. So the orbit of Mercury is the red piece. And so we study this. We sort of look, are we sure, right? Could there be another planet? So maybe the piece is blue in the end. But in the end, if we come to the conclusion that no, there is no other planet, this is a genuine, really thing that happens in the universe, we've learned something very important. There must be a puzzle that is red. And we should search for the puzzle because there's a lot of red pieces that are missing from this other puzzle, right? That's much more interesting than finishing the blue one. And so that's how science works. It's trying to reconcile these inconsistencies by changing our worldview. Right? And I think this is very important because people sometimes say, science is just an opinion. No, it's not. It's a process. It's the outcome determined by a very careful process. And of course, people make mistakes in the process, but in the end, it's self-correcting. And once we have that, we have to accept the conclusion. So we have to assume or accept that most of the matter in the universe is invisible. So it leads to a change in worldview. And that turns out to be very difficult for people. It's so much easier to ignore the piece of the puzzle than to change your view of the world. But that's very important because by changing our worldview, every time we loop through the process, we get closer to the truth. So we have observations, we find inconsistencies, because everything that agrees doesn't tell us anything new. We get ideas, so that's where the creativity comes in. We have to find ways to explain that inconsistency and change the worldview. And that change in worldview then leads to new predictions. We go out and see if we can break that new worldview. And so the best thing that can happen to a scientist is to find out that everything he or she has been doing needs to be changed. Because that's when we learn something new. We get closer to the truth, but we never know whether we've reached the truth. So that's impossible to know. The only thing we know, this is guaranteed to get us closer, but it doesn't tell us how close. And so that's good to sort of contrast what happens often in media, in all the discussions about vaccinations, etc. It's intuition versus science. It's lazy thinking, quick, yeah, I know the answer, right? Expectations, traditions, emotions. It's comfortable and fast, but it inevitably leads to complexity because you need to come up with excuses for why this piece of the puzzle was different than the rest. Science leads to change, sometimes big, sometimes small, but the context is important. Rational arguments are important. We care about facts. And it leads to simplicity, but it doesn't necessarily make us comfortable, right? It can lead to uncomfortable results. It's slow. It's very slow. It's not good for talk shows because somebody says something that is true, and after an hour of careful thinking, you realize that's true, but irrelevant. Right? You could say to any question that somebody asks, tomorrow the sun will rise. It's true, but most of the time it's irrelevant. So that's the difference, right? The tradition is yes, but, and they come with an exception or an option. In science, it's yes, and it comes with an explanation why that is, or a prediction. So, right, you can all swim now. Let's explore the universe. So I said, we have this theory of Newton. We don't need to bother with Einstein for now. We have this theory of gravity, and it tells us everything should move. Nothing can stand still in Newton's theory. We look at the sky, nothing's moving except for the planets. So that was really problematic. So the universe appears completely static, and that is a result of basically our human life scale. It's not a match for the universe. The universe changes very, very slowly because it's so big. But with new technology, like the Gaia Space Telescope, it can measure the positions of stars extremely well. And so this is how we see motion, because angles change with respect to each other. So when you're in a car, you look to the side, things far away appear to stand still, where things that are very close move very fast. But what we cannot do is speed up time, but we can measure these changes in positions better and better. And what you're seeing here is a movie sped up. You're seeing here in a few seconds 300,000 years of motion in the direction of the Orion constellation. And what you see here, everything is moving. So some things in the background appear to stand still. Those are stars very fast, but you see everything in the foreground is moving in all kinds of directions. So the constellations, they move, these stars move also. So if you do a horoscope 10,000 years from now, it makes no sense anymore because the constellations are completely different. So we can do better measurements, and they show that everything changes. And in fact, because of the finite speed of light, the universe, as we see it, is a giant time machine. When we look at distant objects, the earliest galaxies we can see, their light was sent out 10 billion years ago, and it arrives now. We see these galaxies as they were 10 billion years ago. And so we can basically look further back in time by looking further into the universe. It's just like a geologist or a paleontologist. As they dig deeper in the Earth, they uncover older and older fossils, just like when we look at more distant galaxies. So it's a time machine, and we can sort of reconstruct how the universe became to be. And there's a limit. This is the baby picture of the universe. This is the universe when it was 378,000 years old. And there the universe was so hot that everything was ionized. So there were no molecules. It was just protons and electrons. And it created a sort of fog. So this is why we cannot see any further. But that universe is incredibly smooth. You see here blue and red spots. The temperature differences are 1 part in 10,000. Here in the room, the temperature variations are much, much larger than that. So the universe started off extremely, extremely boring. But clearly, that's no longer the case. And that's really one of the big questions. So how did that very boring universe become so complex? Well, you think time. Gravity pulls things together. It turns out, well, no, that's not enough time, actually. So this is where this invisible matter plays an important role. But perhaps more important, who cares about the past? We need to care about the future. So what happens to the universe? I told you it's getting bigger and bigger. Is that going on forever, or will it end? Because then you need to finish your bucket list, right? And so it turns out the past and the future and the present are closely related because they're determined by how much stuff there is in the universe. So if the universe is very heavy, it will expand because gravity pulls and everything, so it slows things down. If I throw something up, right, it slows down and then falls back down. And so that universe will end in a big crunch. So the universe expands, and eventually gravity wins, and the stuff collapses. Or it just keeps on going forever and ever and ever. And so, surprisingly, the question, what's the future of the universe, is the same as asking, how heavy is the universe? So that's what people started to do. But how do you weigh a universe? Like, how do you even weigh the sun? Well, the sun we can measure the mass by looking at how the planets move around the sun. Because we have gravity, but if you move in a more or less circle around the sun, you have a centrifugal force, right? When you take a corner very quickly, you will push outward. And so the same happens for the planets. And so there must be a balance because we are not slingshot into the universe. We've been going around the sun for 4.5 billion years, and we will so for some time. And so gravity and this other force are in balance, and we can use the speed of in this case, the planets, but when we apply it to whole galaxies, we can use the speed of the stars in a galaxy as a sort of gravity sensor. We assume that these galaxies do not fly apart, and so we can measure the motion, the velocities, and when we do that, and this was done in the 70s, there was a big surprise because we know how heavy stars are. We can see the stars, we can calculate how much gravity there must be. And when you do that, you get this dotted curve that as there's fewer stars in the outer regions of galaxies, gravity goes down, and so the velocity should go down. And the big surprise was that doesn't happen. And when we look everywhere in the universe, it doesn't happen. There is much more gravity than we expect, than we can see. And that initially was called the missing matter, and over time it became clear this is something fundamentally different, so that's why we call it now dark matter. And even a step further, we now have a pretty good idea how much mass there is in atoms in the universe, and it's clear we know also how much mass there is overall. And the stuff we're made of, the atoms, the stuff you learn in chemistry class, this periodic table in the chemistry class, that's only 5% of the universe. It's only 15% of the mass. So most of the mass in the universe is this invisible, exotic dark matter. Can't tell more about it because we don't really know. But we do know that it's fundamentally different. So we know there's new physics. So we're in a very special time in science. We know, remember I was saying, Every iteration gets us closer to the truth, but we don't know how close. But the reverse we can do. So we do know that our current theory, the stuff they've been doing at CERN with the Higgs boson, etc., we know that is not the true theory. There must exist a better description of the universe. We just haven't found it yet. But things got really weird in 1998. Because, as I said, so gravity should pull at everything. It should slow down how the universe is expanding. But they discover the opposite. The universe is growing faster and faster and faster, and that led to a new ingredient, and we call it dark energy, which is a given. There are also a lot of marketing people here. It was literally a physicist that tried different terms in conferences and found that dark energy stuck. So that's why we call it dark energy, because it's a nice contrast to dark matter. It's very different from dark matter. We think dark energy is related to a property of space, but it sounds nice, right? It sounds scary. You remember it. All right, so just because it's towards the end of the day, so now is a good time to start thinking about what comes afterwards. So this is a very good model for the universe. So whenever, particularly if you get a glass of Guinness, you can think that's a good model for the universe. Because that froth on top, that's the stuff you know. That's the stuff you see around you every day. The rest, the dark stuff, the good stuff, is the dark matter, dark energy, which is new physics. Like, it's remarkable. We have made all this progress, and still we don't understand 95% of the universe. We really have not a good idea. So it's new physics. It's great to be discovered. Dark matter, of course, has been around for some time. And so we have some ideas what it could be. As I said, this model that they test at CERN, the standard model of particle physics, people already since the 60s have been looking at, this again, just like this theory of gravity, there were conceptually issues, that there are little issues and people start exploring, can we get rid of them by new theories? And interesting, many of these new theories predict the existence of dark matter. So this is why dark matter, people's like, yeah, sure, we haven't seen it yet, but people are trying to discover it. But we have some idea that it's a new particle, a new fundamental particle. So that's why it's some sort of beer. So it's also, brewers are very interested in this stuff, so they make beers called dark matter. But we don't, so many flavors, but we don't know yet, right? So we don't know which is the right one, but we have a fairly general idea. Dark energy is much trickier. It could be beer, it could be some fertilizer, or it could be something you really, really should not drink. And so the only way forward, and we're in this odd regime when, right, normally we have data telling us what the new theory should be. In this case, we're really data starved, because you might say, well, that's a lousy job. You discovered 95% of the universe only recently, like how slow are you? It's because these effects are incredibly subtle. It really takes the progress in sensitive telescopes that we can peer deep into the universe to discover this. And so to make progress, we need to get better measurements, more data, but the question is what kind of data? And so that's why I'm very excited, because hopefully, literally a month from now, this satellite will be in space. It's Euclid, something I've been spending now 12 years on, and it's almost ready to go. So this is a satellite designed to explore the dark universe. Tomorrow I'll talk a little bit more about that, but I just want to give you an impression of how much better it is. This is what we can do from the ground, with current telescopes from the ground, right? Take a close look. This is the best we can do. This is what we expect Euclid to look like. So this is a picture taken with the Hubble Space Telescope. Euclid is about the same quality. The Hubble Space Telescope, I hope you've heard of it, has been operating for 30 years. has been taking beautiful pictures. It takes us a week to take the same amount of, cover the same amount of area, and then we continue for 6 years. So we have this kind of data we're used to over a decent part of sky, but we'll have this over a vast amount of sky. Right? And I hope you agree that if you compare that this is not so good as this. Right? This is much sharper. So it's really exciting. So in February, this is the first time, even though I've worked on it for a long time, that I saw it for real. It was an amazing experience. You go around the corner, you see an object, and you're like, I know that one. It was really an amazing experience. It was undergoing the final tests. And then in April, it was put on a boat, shipped to Florida, and then hopefully, as I said, less than a month from now, it'll be launched into space on a Falcon 9 by SpaceX. So it's really, really exciting times. I've canceled my summer holidays because I'm afraid there's lots of things we need to do after launch to address this. So just to quickly summarize, this is sort of in a graphic our current view of the universe. I haven't talked about the very, very beginning. There's a lot of speculation there as well. But we started off with this very, very small universe. Everything in an unimaginably small bit. Then we believe it just literally exploded very quickly, became very, very big. Then so that part is all still speculative physics. So this is why we want to understand it, because it allows us to extend our theories of physics. Then something we don't quite understand either. The first stars formed, the first galaxies, things happened. But as I said earlier, to make the complex universe we see, this dark matter played a very important role, because it's the dark matter that formed the skeleton of all the structure in the universe. So even though you've never sensed dark matter, right now dark matter is flying through your body, don't worry, it will do anything, literally. To some extent, we wish it did, because then we could detect it, but let's make our lives more difficult. It flies through your body, but it's essential. Without the dark matter, we would not be here today. So this invisible material is essential for all the complexity we see around us. And then more recently, this dark energy, which is indeed a bit more scary, because it makes the universe grow so fast that soon, in about several tens of billions of years, we can't see anything. Everything will have moved away from us. So then astronomy will get very boring. So now is also the time to do these experiments. So it's a really exciting time to really try to link that whole history of the universe together. So this is dramatically different, right, from this TikTok universe we started off with a few hundred years ago. And one of the things that has happened, right, we started with this TikTok universe, then we learned, okay, we're in a galaxy, right? The discussion of what a galaxy is, it was resolved only 100 years ago. Then we discovered there's many galaxies. We're just a planet around a relatively ordinary star in an ordinary galaxy. And now the ultimate question is, are there perhaps more than one universe? And this is linked to ultimately the question, why are we here? Why is there a universe? Because you can solve that question from the beginning by saying there's been an infinite number of universes. There will be an infinite number of universes in the future. They have nothing to do with us. We're just here in our universe. But it would be phenomenal if we can sort of make that link and find evidence that there might be more than one universe. And I hope that you have now changed your view of the universe. In particular, that you now have a better sense that how science works, and that science and what I said is not an opinion, but a real, amazing worldview, the result of basically a century of observations. Thank you.